Good afternoon.
Good afternoon. We can hear you.
Thank you. So I'm Dr. Maria Zimzami from Sultan Moulay Slimani University. Professor Shafi Mariam, are you here? Professor Malawi Abd Samad, are you here? The participants are here.
Yes, I am.
Yes, we are here.
Okay, so we will start our session named Control Mechatronics. Dear authors, I hope you and your loved ones are in good health. Welcome you to be with us at this international conference. I want to congratulate you that your paper has been accepted for presentation. In order to make our session a success, I would like to ask you to follow a few guidelines. First of all, the presentation must be in English. Secondly, the time allocated for each speech is 15 minutes, including questions. Indeed, you have a maximum of 12 minutes for the presentation. Please disable your microphones unless you are the presenter and during questions. In this session, we have 3 presentations. So we will start with the presentation number 3, then presentation number 30, and we conclude with the presentation number 148. Have fun and enjoy the scientific events. Please, we must follow the order. You have the floor, Madam Yusra Karim or Mr. Shawkawi Abdelaghni.
Thank you. So I will share my presentation.
Okay, thank you. It's okay now. You can start your presentation, please.
Okay, thank you. Thank you for giving me the opportunity to participate in this conference. So I will present my work entitled Human and Organizational Factors Maturity Model Development and Implementation in Construction Industry using Fuzzy Comprehensive Evaluation Method. I'll begin by an introduction. After a literature review, then I will describe the proposed maturity model. In methodology, I will explain the AHP and the Fuzzy Comprehensive Evaluation method utilized in this work. Then, in case study, I will present and discuss the results obtained, and finally, the perspectives of this work. The prevention of process accidents was first based on the technical design. The work of engineers made it possible to better preserve the integrity of the installations in unusual situations. The CVSO and 3 Mile Island accidents gave rise to stricter regulatory requirements and then the implementation of safety management system. These technical and organizational actions have led in some sectors to a continuous decrease in process-related accidents, but in many companies, these improvements did not lead to a reduction in failures. Hence, the integration of human and organizational factors in order to pay attention to bottom-up formalism, not only the top-down ones, to ask more questions about the management and the organization, and to consider the reality encountered. Sorry, you can see the presentation, please.
Yes, madam, you can continue.
Yes.
Sorry. And to consider the reality of the situation encountered by the operators. So, due to their effects on health and safety in work, the integration of human and organizational factors is essential to support companies in continuous improvement and reach better human performance. However, the implementation of such an approach that integrates both the organizational and human factors still faces many problems. Organizations wishing to follow this approach have difficulties in finding an effective technique to evaluate the actual situation and determine the appropriate action plan to improve it. So, to face these difficulties and guide companies to best practices, researchers have developed the maturity models that aims to define the current state as is, benchmarking with standards and best practices, definition of the desired state to be, and finally the definition of key performance indicators and improvement action plan. The quality management grid and the Western typology of organizations represent the two principal roots of maturity models. The QMMG was proposed by Crosby. He suggested that the organizations are likely to develop through 5 stages to reach the maximum level of quality for each aspect of the quality management. This maturity grid was adopted and utilized in the software industry. The best known is the capability maturity model, which was created to help software companies in determining the current maturity of processes and the most critical issues for quality progress. Typology of organizations was proposed by Western. He identified 3 types of organizations, each representing a manner of handling the information flow. This typology was extended to 5 levels to allow a precise and subtle classification. These are pathological, reactive, calculative, proactive, and finally generative. The most frequently cited maturity model is that one developed by Fleming, safety culture maturity model. He proposed from the elements listed by the health and safety executive in their human error guidance to examine the maturity of these 10 elements related to safety culture. The 5 are defined as iterative steps through which an organization can evolve: emerging, managing, involving, cooperating, and continually improving. The overall level is obtained by taking the average of the 10 elements levels. Another maturity model is that one proposed developed by the Kale Center in 2015. The human factors maturity model. It was developed to help companies in identifying their actual level of integration of human factors and determining elements to improve. The model defined from the 10 key topics proposed by the health and safety executive 10 specific human factors topics. For measuring the maturity level, the center proposed a card sort method, which consisted of asking the experienced staff to choose one of the 5 cards for each topic. The 5 cards represent these levels: emerging, transitional, planned, proactive, and leading. As I have presented in the literature review, there are several maturity models that, related to human and organizational factors that have been adapted to different sectors like the offshore and mining industry. The current model is built up around the 5 key elements related to human and organizational factors which are critical to better human performance and help to reach a maximum level of safety. The hierarchy scheme contains the 5 factors given by the Rail and Safety Standards Board in their guide Understanding Human Factors. Then we brought out for each factor a set of sub-factors FIG associated, through which we can measure the human and organizational factors maturity in several industries. Design, training, staffing, culture, and working conditions are the 5 crucial elements that can present a major opportunity to improve human performance, reduce the potential of errors, and increase the margin of safety. For assessing the maturity level of these elements, we used these 5 levels described in this table: basic, transitional, rational, planned, managed, and continually improving. From the guide and the researchers, we listed for each sub-factor the good practices that each company must follow to be capable and mature in its management of human factors. For example, when designing the workplace, the company must consider these points. Use the anthropometric data to fit between the body dimensions of the users and the dimensions of workplaces, take into account the biomechanics of the human body, apply principles of components arrangement, consider the environmental conditions. Many measurement methods have been utilized for determining the maturity level in different models before, but they require human judgment, which often include vague and imprecise preferences. So in this paper, in my paper, we suggest the application of the AHP method for calculating the weighting of factors and subfactors according to their human performance impact, then the use of the fuzzy comprehensive evaluation method to assess the human and organizational factors maturity level while taking into consideration the uncertainty and the vagueness of a human's judgment. The AHP is a multi-criteria decision-making approach. It structures alternatives into a hierarchical order according to criteria through pairwise comparisons. So to determine the weighting of our elements, first we construct the hierarchical model and identify relationships between factors and subfactors. We undertake the elements pairwise comparisons according to their effects on an element located above in the hierarchy using the Satie scale. Third, we calculate the relative weights. And finally, we compute the consistency ratio. The fuzzy comprehensive evaluation method is a mathematical method that uses fuzzy logic principles to solve complex and fuzzy decision-making problems. For determining the maturity level, we followed these steps. First, we established the second-class index membership matrix, where Rij is a fuzzy relationship from the subfactors Fij to the evaluation set corresponding to the five levels of maturity. Second, we calculate the first-class index membership matrix R using this formula. And finally, we determine the vector of a human and organizational factors maturity level using this formula and according to the maximum membership degree law. So in our case study, we applied the model, this model that we have proposed in a multinational company while realizing a construction project of mining facility in Morocco. For calculating the factors and subfactors weights, we used the pairwise comparisons were carried out by a group of experts involving different management levels issued from several departments of the organization studied. The comparison matrices obtained are shown in these tables. So using the steps of the AHP, we obtained the weights of factors and the weights of subfactors shown in this table.
Madam Karim,
yes?
Are you
Yes?
hear me? So you have
Yes?
2 minutes left. Please
Okay.
respect the time.
Okay.
Thank you.
So and here we have the second class index membership matrix using the expert's judgment. After we obtained the first class index membership matrix and this vector of maturity. So according to the principle of maximum membership degree law, we obtain the maturity level of the company, which is planned, and we can conclude that the level of maturity of design, training, staffing, and culture is planned, while the maturity level of factor conditions is transition. After assessing the maturity level, the next step for the company consists to move up from the level planned to managed. To this end, it is recommended to establish an action plan based on the results of this study and create a dashboard with key performance indicators related to human and organizational factors. So after, according to the impacts of factors and sub-factors obtained by the AHP and the results of expert judgment, we suggested to the company a set of guidelines in order to achieve the desired situation. And finally, from the perspectives of this work, we suggest to apply the proposed model to other industries to verify if it really reflects the actual situation of the company, and also to compare the results of this methodology with another methodology, like the application of the ANP instead of the AHP, to consider the interdependence among the elements. Thank you.
Thank you, Madam Karim, for your presentation. So the presentation was very clear and well presented. I have just one remark. So the parts of literature review is very long.
Yes. Okay.
It is important for you and for your work to know all these methods and models, but presenting all of them is not important. You know,
Okay.
6 minutes just for this part. It's too long.
Okay. Thank you for
But
the remark.
it was very clear and well presented. Who wants to ask questions? I repeat, please, who wants to ask questions? Do you have some questions for Madam Karim?
I have no questions.
Okay, thank you. You can ask your question, please.
I said no, I have no questions, so we can.
Okay, thank you.
You're welcome.
So we move on to the next presentation.
Thank you. No.
Authors of ID 30. You have the floor.
Yes, I'm here. I will try to share my presentation.
Okay, thank you.
Can you see the presentation, please?
Yes, it's okay for me.
Shall I start?
Yeah, you can, please.
Okay, thank you. Hello, everyone. I hope you are safe and in a good health. I'm Samia Bilasal, industrial engineer and PhD student in mechanical department at Mohammedia School of Engineering in Rabat. I'm here today to present you my work, which is about the effect of profile shift factor on the bending stress of spore gear using the finite element analysis. First of all, I will present you the outline of this presentation. I will start with an introduction about the domain of spore gears, their utility and different parameters. Secondly, I will talk about the bending stress generated on the root of the spore gear teeth, the bending stress formula, the different coefficients of this formula using the Lewis theory and ISO standards. The theoretical results obtained in this part of the presentation are compared with the results given by the finite element analysis using ANSYS Workbench software, which will be discussed on the third part of this outline. At the last part, I will make a conclusion of the steps and the results obtained in this work. Spore gears are the most common type of gears in the industrial field. They are known with their straight teeth. They are also mounted on parallel shafts in different systems and used for a large type of reduction. They are used also for motion and power transmission in various systems. Most of the spore gear failures comes from contact stress and bending stress. The contact stress can be the source of pitting resistance failure, micro pitting, and wear of the materials. The bending stress on the root of the spore gear teeth can lead to tooth damage. Generally, spore gears are mainly characterized by their model M, which unites for size that indicate how big or small the gear is, and the number of teeth, and pressure angle, which present the angle between teeth face and the gear wheel tangent, and the profile shift factor X, which determine the thickness of the spore gear teeth or the high of it. In this study, the influence of the profile shift factor the influence of the profile shift factor on the contact ratio, the load sharing factor, and the bending stress on the root tooth of the spore gear under the load is analyzed using Lewis theory, isostandards, and finite element approach to minimize general stress created on the spore gear system. Now I will talk about the theory of bending stress created by Wilfred Lewis in 1983, which is used in this work to have the theoretical results. His theory is based on assumption of considering a gear tooth as a cantilever beam. Lewis considers a single spore gear tooth subjected to tangential leads on its tips, which leads to bending stress on the root of the tooth. The tangential load is uniformly distributed over the face width of the tooth. He said also that the load is applied completely on the tip of the single tooth of the static at the static mode. All the radial components forces generated because of the teeth sliding friction and the stress concentration are negligible for this theory. According to ISO standards, the maximum bending stress in the root of the spore gear is calculated as follows using this equation. If T is nominal tangential load, B is face width, M is the normal model. YF is the form factor. Is calculated using this equation. Ys is the stress factor. This is the equation to calculate this factor. The Helix factor in this work is considered as 1 because we are working with the spore gear and not with the helical gear. The load sharing factor is calculated using this equation with CR is the contact ratio. The contact ratio will be presented in the second slide. The contact ratio is the average number of pair of teeth in contact at the same time. The beginning and the ending of tooth contact is in the intersection of the two addendum circles with the pressure line. It starts at small a and finishes at a point small b. The tooth profile also interacts with the pitch circle at point A and B. This is the pitch circle. The contact ratio is also the length of the path of contact, divided by the base pitch, AB. For example, a contact ratio equal to 1 and 7/10 means that for 70% of time, two pairs of teeth are in contact simultaneously, and for 30% of time, just one pair of teeth carries all the load. According to ISO standards, this is the equation to calculate the contact ratio equation. X is the profile shift factor. which is linearly dependent on the addendum HA. In this study, we used 3 cases of profile shift factor, which are analyzed. The profile shift factor equal to 0 means that the gear is a standard gear. For the 2 cases, the last 2 cases, the gear is a corrected spore gear. For this reason, a MATLAB code was created giving the following results shown in this table. Results of contact ratio and contact ratio factor. The figure in the left shows the evolution of contact ratio, which depends on the variation of profile shift factor. As we can see, the contact ratio is increasing while increasing the profile shift factor. In the left figure, we can see that the contact ratio factor decreases while increasing the profile shift factor from 0 to 0 and 2 tenths. For the gear generation, the 3D model of the 3 gears is generated on SolidWorks using the involute equation to plot the curve of the spore gear tooth. This table presents all parameters used to generate the 3 gears, which are the model, the pressure angle, number of teeth, face width, material, Poisson's ratio, elasticity factor, and tangential force, which is calculated before starting the simulations. For the 3D models of geometry are imported from SolidWorks with the same parameters except for the profile shift factor. The finite element analysis is used by ANSYS Workbench by software. The material used in this study is the standard steel defined on ANSYS Workbench with different properties, which are density, modulus of elasticity, and Poisson's ratio. To increase the accuracy of the bending stress result, the models of geometry are meshed using hexaedral form of meshing. And for the boundary condition applied to the 3 geometries, we fixed the spore and then we applied a tangential force on the tip of teeth, which is equal to 1122 for the theoretical calculation, and according to Lewis theory and ISO standards, all parameters used to calculate the bending stress are presented in this table, which are the form factor, stress factor, helix factor, nominal tangential load, half face weight, and operating pitch diameter. The form factor and the stress factor are calculated using the DIN 3990 norm. Now I will present to you the results of bending stress using the ISO standards and the numerical simulation by ANSYS Workbench. For profile shift factor equal to 0, which means a standard gear, we have the highest value of the bending stress equal to 81 and 945 megapascal for ISO standard, and 89 and 585 megapascal for ANSYS Workbench. For profile shift factor equal to 0 and 1/10, the results of the bending stress by ISO and ANSYS decrease. And for profile shift factor equal to 0 and 2/10, the bending stress results continue to decreasing to the minus value of bending stress for ISO and for ANSYS workbench. As conclusion, we can say in Spore Gears, the shape of the teeth is purely related to the bending stress and on the root of the Spore Gear teeth. The maximum bending stress generated on the root of the Spore Gear teeth depends directly on the profile shift factor value when it changes from 0 to 0 and to 10th. We can also say that we used the same number of teeth, the same angle pressure, and the same model for the three gears used in this presentation. The bending stress generated by ANSYS workbench decreased by 7%. At the same time, the theoretical result drops by 5%. And the bending stress results generated by ANSYS workbench are generally higher than the theoretical results. That's because of the numerical simulations give more accurate results because they are very developed, and hence the theoretical result by Lewis theory depends on a lot of assumptions and empirical results based on only on experiences and history. Finally, we can say that the higher the profile shift factor of the Spore Gear teeth is, the lower the bending stress on the tooth root can be, which is very interesting in terms of minimizing the pitting failure, raising the life period of the material, and reduce risks of complete system damage. Here is some references used in this study to come up with different results, and thank you for listening.
Thank you, Madam Samia.
You're welcome.
So the presentation is well presented, well detailed. So congratulations.
Thank you so much.
I have just one question. So
yes, I'm listening.
For the second part, the part for bending stress.
Yes.
So I didn't understand your example for the calculation. It concerns the calculation of contact ratio.
Of?
Contact ratio.
Contact ratio. Okay. Yeah. A contact ratio is used to calculate the contact ratio factor.
Yeah, but I want to understand the example. You give the example.
I used a MATLAB code to calculate it. I used an algorithm describing the equation on MATLAB, and I calculated the contact ratio, then the contact ratio factor, then the bending stress, and finally I come up with the results. If you didn't understand the equation or what exactly?
Yeah, the equation. Yeah. You give an example after giving the equation. You give an example. I want to understand just your example.
My example, okay. I will share again the presentation.
You can share, yeah. You can share your screen, please.
Okay. Here is the equation.
Yeah. Yeah.
First of all, we have to determine the number of teeth, which is 24 for this case. Then the addendum factor. The addendum factor is 1 plus the profile shift factor. The addendum is 1 plus the profile shift factor multiplied by the model, which is 2 and 5/10 for this case. The pressure angle for this case is 20 degrees. So first of all, we calculate N, which is the number of teeth divided by the addendum factor, which is 1 plus the profile shift factor. we calculate the addendum factor, which is the addendum HA divided by the model. So then we calculate U, which depends on the number of teeth and the pressure angle for the first gear and the second gear if we have two gears in contact. If we have just one gear, so we used just Y1 and U1. Then we calculate the contact ratio theoretically using this equation. So we have just first of all to define the number of teeth, the pressure angle, the model, and the profile shift factor. Then we calculate the contact ratio using this simple equation.
Okay.
I use a code MATLAB. I give the code the number of teeth, the pressure angle, and then the model, and then the code give me the results about the contact ratio using this equation. Alpha here is the pressure angle, n is the number of teeth divided by y, which is 1 plus the number, the 1 plus profile shift factor, which goes from 0 to 0 and to 10. Is it a little bit clear or?
Okay, it's clear, madam. Thank you. So,
You're welcome.
who wants to ask questions, please? I think there is no question.
There is no other questions?
I don't think so. So we move on to the next presentation.
Okay, thank you.
Thank you.
You're welcome.
Mr. Najih Youssef, you have the floor. Please activate your microphone and share your screen.
Okay.
It's okay now. You can start your presentation.
Okay, thank you. So, hi, Professor and audience. I'm Najih Youssef, Doctor of Mechanical Engineering, and I'm going to present you my presentation entitled Mechatronic Control Model of a Novel Variable Speed with Turbine Concept with the Power Splitting Drivetrain, a bond graph approach. So we talk here about the aims of this study. So we talk firstly the design of mechatronic model of the wind turbine and gearbox component, using of course a new concept of velocity composition in order to establish a stabilization model of the wind turbine, modeling and control by bond graph of a new wind turbine concept with the power separation kinematic chain, theoretical development of planetary gearbox control scheme for a wind turbine. So, introduction. Wind energy is an indirect form of solar energy. This clean energy, which is become less and less expensive with technological progress, allows decentralized electricity production with low greenhouse gas emission. So the objective of this study was to create a model system based on a direct current motor, thus stabilize the generator's rotational speed. The purpose of this new system is based on the controllable motor transmission technology. By adjusting the torque, the generator always operates at the constant desired speed to maximize wind energy, while the wind speed is highly variable. Also, we have tried to establish a system that stabilizes the wind speed, which is always variable. In this case, we have established a control system that converts the output of the turbine into two components to give a stable speed in order to maximize the power generated by the wind turbine. So we make first a modeling system for all the component system, and we talk here of the wind turbine system. The wind turbine studied in this work is a 5 megawatt horizontal axis with the variable speed. The main diagram of the wind turbine with power split transmission are presented in this figure, where the mechanical energy is divided by the planetary transmission into two components. One of them is connected to the main generator, which is directly connected to the grid, and the other is connected to the interface via the control motors. Secondly, modeling of the mechanical system. So the mechanical model include all the mechanical components of our wind power system. The tower and the drivetrain divided into two flexible structures. The kinematic chain of this system consists of the turbine rotor, the transmission system gearbox, and the generator of the wind turbine. It is modeled by a multi-body system which contains several degrees of freedom. And this figure shows a synoptic diagram of the three mass of our system. We also talk about the planetary gear using in the system on mechanical system. The power is transmitted by the planetary gear differential, which with the epicyclic gear and the differential. The schematic representation of this epicyclic differential is shown in this figure. The angular velocities are indicated by the symbol omega, the rho by r, and the indices C, S, P, and R represents respectively indicate the sun, the carrier, the planet, and the cycle. The angular velocity of the planet seen from a fixed frame attached to the gear wheel is the sum of the angular velocity of the carrier and the angular velocity of the planet seen from a frame attached to the bracket. So here we present the complete system. The system shown in this figure regroups the different subsystems presented in the previous sections, which are combined in a global system. The aerodynamic subsystem inputs are coupled with wind source, the output torque. The aerodynamic subsystem represents the input of the mechanical subsystem applying to the turbine rotor. The output of the mechanical system is the output torque of the aerodynamic subsystem, which represents the input of the electrical subsystem. The generator speed control is performed by servo motor, which will be controlled by a PE controller. So, in this section, we present the result of simulation using the 20sim software. As shown is this figure, we have applied a variable wind speed, wind turbine rotor speed. The first simulation has been performed on the generator and servo machine speeds. Here we present the wind speed and the rotor speed and also the speed of servo motor. We notice that the generator speed is almost variable as shown in this figure. Moreover, the speed of the servo machine varies according to the variation of the wind speed. This explains the great stability given by the PE controller on the speed. And this figure shows also the result of the simulation result of the power It can be seen that the turbine generator power can be limited with their rated values to achieve optimum output. As shown is this figure, the turbine system follows its reference value will show that the capture of the optimal wind energy is achieved. With the PE controller, we notice that the power remains constant and the servo machine operates in continuous operation mode to compensate for the speed and the torque deviation of the wind turbine. So, conclusion, in this work, a structure and model strategy by PE controller of 5 megawatt wind turbine was proposed to stabilize the speed and also reduce the loss and the maintenance caused by the electronic converters. We implemented a planetary gear to improve the performance of the wind turbine and also to avoid introducing a standard gearbox. The PE controller is set up on system including the servo machine for optimal production point. The system was modeled by mechatronic approach using bond graph representation. The simulation results show a good performance of the wind turbine with high speed stability and then on optimal production of electrical energy. Thanks to the simulation result, the proposed power split system can be used in the areas where there is no uniform wide wind profile in order to have a well-optimized production. And thank you for your listening.
Thank you, Mr. Najih. So your presentation was very clear and very short also.
Thank you. Thank you.
The subject of your presentation is very interesting.
Thank you.
I want to ask you one question, please. So what is the added value in your work?
If you have no problem, est-ce que je peux parler en français?
Try to answer in English. If you can't, you can use French. Okay,
so the main object is to have je parle en français, c'est mieux, si vous voulez, bien sûr. L'objectif principal, c'est d'avoir un profil stable du vent, parce que la turbine éolienne sont généralement exposées dans des zones où on a un profil de vent qui est variable. Et ça cause bien sûr beaucoup de problèmes dans la production de l'énergie. Alors l'objectif, c'est quoi? C'est de mettre un servomoteur qui va soit augmenter la vitesse ou bien diminuer la vitesse selon le profil du vent, selon la vitesse de la turbine. Et c'est ça l'objectif. D'une part, de stabiliser la vitesse et d'autre part, pour avoir une production de l'énergie optimale.
D'accord. Et donc, je vous réponds en français. Et donc, à votre avis, est-ce que l'approche que vous suivez permettra d'améliorer davantage ou d'éviter cette problématique? Parce que, comme vous le savez, normalement, vous avez fait une étude bibliographique du sujet, ça c'est très clair. Et oui. Il y a beaucoup de personnes qui travaillent sur l'éolien. C'est pour ça que j'ai dit que c'est une thématique très, très, très importante. Donc, oui. Et c'est d'ailleurs la raison pour laquelle j'ai demandé votre valeur ajoutée à ce travail. Oui. Donc, comment vous estimez votre position dans cette thématique par rapport aux travaux déjà réalisés et qui sont en cours?
Oui. Normalement, les travaux qui sont déjà étudiés, qui sont en cours et sont déjà effectués, ils utilisent vraiment un encombrement des convertisseurs électroniques et ça engendre vraiment beaucoup de maintenance et ainsi de suite. Donc, nous, c'est pour la première fois que nous avons utilisé et modélisé ce système grâce à un système qui va diviser la puissance en deux. Je ne dis pas que vraiment ça va donner une valeur ajoutée très, très importante, mais quand même, il va stabiliser la production et aussi la vitesse. Et vraiment, nous avons utilisé ici juste un contrôleur PI. C'est juste, nous avons utilisé peu d'électronique, pas beaucoup. Et vraiment, le résultat que nous avons montré dans le résultat de la simulation a vraiment montré qu'il y a une stabilité, une grande stabilité en utilisant ce système. Donc ça, c'est notre valeur ajoutée. D'accord.
D'accord. Donc, si j'ai bien compris, normalement, vous allez joindre l'optimisation à votre travail parce que, comme je suis spécialiste en optimisation, c'est le champ sur lequel je travaille.
Oui.
Donc, je trouve que normalement, faire appel à une méthode d'optimisation, peut-être pour effectuer des tests, pourra faire l'affaire, genre, pour voir ce que ça va donner. Peut-être que ça pourra améliorer davantage vos résultats. D'accord. Donc, I wish you good luck. Thank you.
Thank you for all, cher professor.
Who wants to ask questions? Please, there is some questions. So thank you, Mr. Nazir.
Thank you for you. Thank you.
And congratulations for you all.
Merci beaucoup, merci. Je vous remercie.
So I will end this session. Thank you for all authors for your presence and for sharing with us this your works.
Thank you, Professor.
You're welcome. So I will end this session. You can leave if you want.
Thank you, Professor.